Okay. See, next we'll go for one more concept, a very important concept called as electric field. See, electric field means in general, let us say that it is the space around a charge, in which if any other charge is placed, then it will experience the influence of the original charge, or it will get affected by the original charge. It means the space around a charge in which the influence of a charge is experienced is said to be electric field. We'll take one very general example for this to know in detail about it. See, if I say, let us consider we have put a campfire here. This is a campfire. Okay, we have put a campfire here. In the surrounding of this campfire, if I stand at a distance of 1 meter or 2 meter from this campfire, I can get influenced by its heat. I can experience the heat of that campfire when I stand in its surrounding at a radius of either a meter or 2 meter. Then I can experience its heat. I can experience the influence of that campfire. Instead of standing in this surrounding, either in a meter or 2 meter surrounding, if I stand somewhere far away from this, at a distance of some 10 meters, if I say, can I get influenced by its heat? No, now I will not get influenced by its heat. That's why the space around this, where I can experience the heat of this campfire, where I can get influenced by its heat, that space is said to be the thermal field of this campfire. Thermal field of this campfire. It means I can experience its influence, I can experience its heat in that space. Then only that space is said to be its field. In the same way, if I say, if there is a charge present here, called as Q, then the space around it, in which when another charge is placed, will experience a force by that charge. If any another charge placed in the surrounding space of this original charge gets influenced by that original charge, influenced means it has to experience a certain force, either attractive or repulsive. So if it experiences any kind of force in this space, then this space is said to be electric field of this charge. Wherever you want, you can keep it. If you want, you keep it here, you keep it here, you keep it here. Wherever, if you keep this charge Q0 in this space, then it will start experiencing a force due to this original charge. Then this space in which that another charge will experience the influence of this charge, then that space is said to be electric field. If I keep this charge far away from this original charge, then it will not experience any kind of force. Then it is not said to be in the electric field of that charge. Okay, that is said to be electric field. See, this is all about general discussion of electric field. Next step, we'll go for mathematical expression for this electric field. How to define this electric field mathematically? See, electric field is mathematically defined as electric field at a point is defined as electrostatic force experienced per unit positive test charge placed at that point. Electric field is defined as electrostatic force experienced per unit positive test charge placed at that point. It means electric field is defined as electrostatic force per unit positive test charge placed at that point. E is equal to F by Q0. This is the mathematical expression for electric field in terms of electric force as well as the test charge. See, this electric field is also called as electric field intensity or electric field strength. In some questions, the wordings used will be different. Either electric field or electric field intensity or electric field strength. Okay, so we got to know what is electric field as well as mathematical expression for electric field. Next, what is the SI unit of electric field? See, SI unit of electric field is either Newton per coulomb or volt per meter. These are the SI units of electric field. So the SI unit of electric field are volt per meter or Newton per meter. See, dimensional formula of electric field is M1 L1 T raised to minus 3 E raised to minus 1. This is the dimensional formula for electric field. See, electric field is a vector quantity. Vector quantity means what? It should be having magnitude as well as direction. We have discussed in scalars and vectors in the first year. So, electric field means it is a vector quantity. It is not a scalar quantity, it is a vector quantity. Vector quantity means what? It should be having a certain direction. Then what is the direction of this electric field? See, electric field is having a certain direction. If it is a positive charge, electric field will be away from the positive charge. This is the direction. If it is negative charge, electric field will be towards the charge. It will be towards the charge. If it is negative charge, electric field will be towards the charge. This is the direction of electric field. So if it is positive, electric field will be away. If it is negative, electric field will be towards. This is the direction of electric field. Next, significance of electric field. What is the significance of electric field? See, significance of electric field means at a point, if you want to know what is the force experienced by a test charge placed at a point, then if we know the electric field at that point, and whichever charge you are placing there, let me take it as Q0, then we can calculate what is the force experienced by this charge at that point. So that is significance. See how Fe is equal to, we know that it will be F by Q0. Then we want to calculate the force now. So force will be equal to E into Q0. It means by knowing electric field at a point, we can calculate the force experienced by a charge which is placed at that point. At a certain point, if I know how much is the electric field, and if at that point if I place a charge called as Q0, then by using this formula we can calculate the force experienced by that charge at that point. That is the significance of electric field. Is this clear? See, till now we used a word called as test charge. Q0 means we called it as test charge. So what is this test charge? We'll be using two types of charges now. We'll be using two types of names of the charges now. One is source charge and then another one is test charge. So let us see what is source charge and test charge. See, source charge means, first one is source charge. Source charge means the charge which produces the electric field. Source charge means the charge which produces the electric field. Let me take it as Q. Second one is test charge. Test charge means the charge which tests the source charge. Okay, the charge which experiences the electric field of the source charge. That is test charge. Test charge is represented by Q0. See, previously we have discussed that if we consider a charge called as Q, then now this is the space around the charge in which any other charge will experience a force. That's why that space around this charge is said to be electric field. This electric field is due to this charge. So this charge is said to be source charge. This is called source charge because it is producing the electric field. So the charge which produces the electric field in its surrounding is called source charge. And to experience the force of this electric field or to test that electric field of that source charge, we use one more charge which we call it as test charge. This is just to test. This charge is just to test. So this test charge Q0 will not affect the electric field of that source charge. It will not affect this source charge. It will just test the electric field of that source charge. Okay. So source charge means the charge which produces the electric field, and test charge means the charge which tests the electric field of the source charge. That is the difference between source as well as test charges. Next we'll go for electric field lines. See, electric field lines are the imaginary lines which are drawn along which a positive small charge would tend to move if it is free to move. These are the imaginary lines which are drawn along which a positive test charge would tend to move if it is free to move. So when a positive charge, a small positive charge is left free to move, and if it starts moving in a certain direction, in that direction we have to draw an imaginary line which is called as electric field lines. So let us see how to draw the electric field lines for different types of charges and different arrangements of the charges. See, electric field lines for a positive charge means greater than 0. Here is the positive charge. While discussing about the direction of electric field lines, we have told that electric field is away from the positive charge and towards the negative charge. Here we are drawing the electric field lines for a positive charge. For a positive charge, electric field lines will be outwards, radially outwards. They will be moving away from the charge. So this is the direction of electric field lines for a positive charge. It will be in all directions, and it will be away from the charge. So this is electric field lines for a positive charge. Next, electric field lines for a negative charge. And we already know that electric field lines for negative charge will be radially inwards. They will be moving towards the charge. Here they were moving away from the charge. Here they are moving towards the charge. So electric field lines for positive charge is radially outwards. Electric field lines for negative charges radially inwards. Next, we'll go for electric field lines for two positive point charges. Fine. So the electric field lines for two positive point charges. See, if these both are positive, it means they are like charges. Like charges means there will be a repulsive force between them. That's why the field lines will get repelled. Fine. But both the charges are positive only. Positive means we have to show the field lines outwards only. We have to show them radially outwards only. So all the field lines of this charge as well as this charge will be radially outwards. They will not be towards the charge. They will be away from the charge. So this is how the field lines will be for two positive point charges. Similarly, if we go for an electric dipole means it is the arrangement of two equal and opposite charges. Here we are taking one is positive and another one is negative. So for an electric dipole, there are two unlike charges now. Unlike charges means what type of force will be in between them? There will be a force of attraction in between them. Here it was the force of repulsion. Here it will be force of attraction. That's why the lines should be shown in this way. The electric field lines should be radially outwards from positive charge and radially inwards to the negative charge. So all the lines which are coming from positive charge should be outwards, and all the lines which are coming towards negative charge should be inwards. So here the directions should be shown in this way. This is the electric field lines for an electric dipole. Right? Okay. Next we'll go for properties of electric field lines. Important properties. So properties of electric field lines. And that first one is electric field lines are smooth curves without any breaks. First property is electric field lines are smooth curves without breaks. See, we have seen the electric field lines in the previous concept. If I want to draw the electric field line for a positive charge, then the electric field lines will be like this. Okay, they will be radially outwards. But nowhere the electric field lines will be broken. They will be continuous smooth. Nowhere they are broken. Okay, if we are taking a dipole, then the electric field lines will be in this way, but they will not get broken anywhere. So the electric field lines are continuous smooth curves without any breaks. Okay, this is the first property. Second property is electric field lines start from positive charge and end at negative charge. They will start from positive and they will end at negative. See, if there is a dipole, this is a positive charge and this is a negative charge. If an electric field line starts from positive, it will end at negative. That's why field is said to be away from positive and towards negative. Away from positive towards negative. So the field line will start from here and it will end at here. But it will not return again from negative to positive. It will not return. Okay? It will start at positive and it will end at negative. So all the electric field lines will start from positive and end at negative. This is second property. Third property. See, electric field lines will never form closed loops. Never form closed loops. See, closed loops means what? As I told you that when there is a dipole, this is a positive and this is a negative charge. If an electric field line start from positive and end at negative, then it is correct. But we know that electric field lines will start at positive and they will end at negative. They will not return back to positive from negative. If they return back from negative to positive, then it will form a closed loop. But it will not happen because here the rule will go wrong. Here it shows that it is coming towards positive and it is going away from negative. It is not possible. Only field lines will be going away from positive and they will be coming towards the negative. So it starts at positive and ends at negative. It will not come back from negative to positive to form a closed loop. That's why the electric field lines will never form a closed loop. This is the third property. Fourth property is, if there is a single charge means a single isolated positive charge or a single isolated negative charge. If it is a single positive charge, the electric field lines will start from positive point charge and they will somewhere end at infinity. If there is a single negative charge, the electric field lines will start from infinity, somewhere from infinity, and they will end at negative charge. So for a single charge, electric field lines will either start from infinity or end at infinity. So for single charge, fourth property is for single charge, the field lines will either start or stop at infinity. Okay, this is the fourth property. Next, fifth property is the electric field lines or tangent drawn to the electric field lines at any point. Tangent drawn to the electric field lines at any point will give you the direction of the electric field at that point. Say if this is an electric field line now, if I want to know what is the electric field direction at this point, what I have to do? I have to draw a tangent at this point. If I draw a tangent at this point the electric field is said to be in this direction. If I want to know the direction at this point, let me draw the tangent here. This is the direction of electric field. At this point, the direction of electric field is like this. So at any point, if you draw a tangent to the electric field line, at that point, the tangent will show you the direction of the electric field line. So the tangent at any point on the electric field line will give you the direction of the electric field. Fine. This is fifth property. Next, we'll go for the sixth property. See, sixth property is electric field lines will never intersect. Intersect means they will not cross on one another. So the sixth property is electric field lines will never intersect. Okay, fine. They will not intersect. We are clear about it. But why they will not intersect? They will not intersect because, see, for example, if here I say the two lines are intersecting each other. These are the two electric field lines and they are intersecting at this point. At the point of intersection, if I draw tangents to both the lines, to both the electric field lines, if I draw the tangents, then at a single point we are getting the direction of electric field in two ways. At a same point the electric field is having two different directions. It is not possible. Okay, there will be only one unique direction for electric field at one point. That's why if the electric field lines intersect at a single point, the direction of the electric field will not remain unique. Because of this reason, the electric field lines will never intersect. Okay, this is the sixth property. For the seventh property now, see, electric field lines will always be normal to the surface of conductor. Okay, electric field lines are always normal to the surface of conductor. See, how normal to the surface of conductor means how? If this is a plane conductor which is positively charged, let me say this is the plane conductor which is positively charged. See, for this conductor, electric field lines should always be normal like this. Okay, normal means it has to be perpendicular to the surface of the conductor. It cannot be like this. Okay, the electric field lines will always be normal to the surface of conductor. Okay, so this is how the electric field lines should be shown. And since this is a positively charged conductor, the electric field lines will be outwards or away from that conductor. So the electric field lines are always normal to the surface of conductor. Whichever shape body it may be, the electric field lines will be always normal. It may be positive or negative, that is secondary, but field lines will always be perpendicular, will be normal to the surface of the conductor. Well, this is the 7th property. We'll go for the 8th property. See, electric field lines will never enter or pass through a conductor. Will never enter or pass through a conductor. Okay. Why the electric field lines will not pass through a conductor? Because for any charged body on which the charges are in equilibrium, for any charged body for which the charges are in equilibrium, the electric field inside that conductor will be zero. Electric field inside that conductor which is charged, on which the electric charges are in equilibrium. Okay, on such conductor, inside that conductor electric field will be zero. That's why the electric field lines will not pass through the conductor. Okay, the electric field lines will not pass through the conductor. That is 8th property. Next, 9th property. See, the relative closeness of the electric field lines, represents or tells us about the strength of the electric field. Relative closeness of the electric field lines will tell us about the strength of the electric field at that region. See, in a region, if the electric field lines are very close to each other, then here the electric field is said to be strong. If the field lines are very close, then the electric field is said to be strong in that region. If the field lines are far apart, okay, if in this way, if the field lines are far apart, then electric field is said to be weak. Here the electric field is said to be weak if the lines are far apart. Okay, if the lines are close to each other, then the electric field is said to be strong. If the lines are far away from each other, electric field is said to be weak. Next, see, if the electric field lines are parallel and equally spaced, gap between each two lines should be same, then that electric field is said to be, uniform electric field. This is said to be uniform electric field. Uniform electric field means electric field lines will be equally spaced and they will be parallel to each other. Then it is said to be uniform electric field. Well, so this is the 9th property. We'll go for the last property now. That is 10th property. See, the last property of the electric field lines tells us that the electric field lines have the tendency to contract lengthwise and expand laterally. So the 10th property is electric field lines have the tendency to contract lengthwise and expand laterally. So what is this contract lengthwise and expand laterally? See, contracting lengthwise means it will explain us about the force of attraction. Attraction it will explain. And expanding laterally means it will tell us about repulsion. See how it is possible. See, if this is a positive charge and if I keep a negative charge here, the electric field lines will be like this. They will start from positive, they will end at negative. There should be an attractive force between them. So, attractive force means they will start moving close to each other. If they move close to each other, what happens for these lines? These lines will not get folded like this. They will not get folded like this. Okay, they will get contracted. The shape will remain same, but the length will get contracted. So what happened? The force of attraction is explained by what? By the contracting property of the electric field lines.